From here, I'm going to set up my Gauss's law and say that Q enclosed is equal to epsilon naught times the flux. Let's handle the Q enclosed first. I see a insulator that has a total charge density of rho. It says it was uniform, so I'm just going to use rho here in place of the actual charge density. I can calculate the charge density later. I'm just going to use this for now. Is everybody okay with that? Because that means the Q enclosed has to be rho times whatever the volume enclosed is. And the volume enclosed is this volume, which has to be 4/3 pi little r cubed. Now, I can't leave this in my answer. I will have to get rid of this later. And they didn't give me this, but they told me the total amount of charge, and they told me the size of the original insulator. So I'm sure I can figure that out. Probably something like, and I'm looking at the people with the confused look on their face, probably something like this is the charge density. Total charge divided by total volume. So all of you with the confused face, stop it. You have to do this on your own. Don't wait for me. Okay, moving right along, let's do the right side. The right side is going to be the calculation of flux. The electric field and the area are in the same direction, so the dot product is 1, cosine of 0 degrees. The electric field should be the same value everywhere on the circle, so it's a constant, meaning I can rewrite this as epsilon naught times E times the integral of dA times the cosine of 0 degrees. No, you don't have to write all of this out. I'm just making sure I've handled everybody's question and also trying to do the same thing I would do in mechanics, where I always draw the stupid arrow with the plus sign above it to make sure you've remembered that up is positive or that you're choosing a direction for positive. I'm doing all of this to remind you that there's a dot product there. Don't forget about it. And I'm also trying to remind us that we need to consciously consider whether the electric field is a constant or not. Those are the reminders I'm trying to make. So for those of you who are a little bit more unwilling to see that, I'm trying to just rub your noses in it a little bit. Now all that's left to do is to consider that this says add up the entire surface area for a sphere. Okay, that would be the surface area of a sphere. The sphere in question here is the green Gaussian surface. So that will be 4 pi r squared. And yes, you have to know these things. So we've handled the flux side and we've handled the Q enclosed side. I see no reason not to dump this into rho and get Q over 4/3 pi big R cubed times 4/3 pi little r cubed. And now solve this for the electric field. Some stuff's going to cancel out, like the 4/3 pi and the 4/3 pi, the r squared and 2 of those. And it looks like I'm going to be left with E equals Q over 4 pi epsilon naught times r over r cubed. Grouping them out, I guess I could put the r cubed on the other side. The idea is I want to make sure that we understand that the only actual variable that matters here is the r. This is all a constant, but this is the part that indicates where we are inside the circle. That's what r is. So as r increases, the size of the electric field also increases. Makes sense. As r increases, there's more charge contributing to the electric field. As r gets smaller, there's less charge contributing to the electric field. And if you're at the very center, you'd be pulled equally in all directions. The electric field should be 0. All right, that was A. Would anybody like to see part B? All right. Anybody like to see part C? Interesting. That part surprises me. Was it hard for you to say electric field is 0? Okay, good. So, just joking. Now determine the electric potential at the following locations. Does anybody need to see A or B here? Okay.
Just a question. No, I'm not confused about it. A and B are the same, right?
A and B are the same.
Okay.
Like I reinforced in class yesterday, A and B are the same. It should be whatever you got for A is the answer for B, not the reverse. Well, I mean, it could be the reverse, but you get the answer for A first. Yes, Gabby?
Just to clarify as well, for the answer for A, your number for like your distance, would that be 3R? Okay.
What's that? Yes. So I would think the answer for A, without doing the works, I really don't think we have to do much work unless it says derive and it says determine. So, oh, by the way, I just added that. That was not in the original question. I added to reinforce talk about yesterday. The original question was just the first A, B, and C, and then D and E. So, but all you would have to do is V equals, and this we're going to have, now, careful, the total charge is Q plus Q, right, because the conductor is charged, over 4 pi epsilon naught times 1 over 3R. And it stays that potential even when you go to the inside, which is funny because technically a lot of you would think, well, there's less charge now inside when I go from that outer ring to the inner ring, but that's not what electric potential is like. It's about how much work it would take to go from the outer side to the inner side, and the electric field is 0 inside, no extra work is done, so the electric field doesn't change, so the work done is 0, so the electric potential doesn't change. It stays this amount. Yes, sir?
Now, say that you were to go from R equals 2R to directly closer to the insulator, would that then change the integral that you have to do?
Yes. And you'll notice I didn't ask that one. And that was purposeful. For 2 reasons. The electric field is 0 till you exit. When you do the other part, the other Q still has been contributing to this. But all you're going to do is get a new term that will add to the electric potential. The electric potential is not a vector. So assuming that it takes more work to go from 2R to R, you'll just add that term. So you would actually just be doing the integral of E dot dr from 2R to R. So this part would only have capital Q in it. It wouldn't have the Q from the outer shell because you're not doing work against that charge anymore. But I didn't ask that question. And I don't know if they would ask it on the exam or not. I haven't seen a question like that. So, would anybody like me to do question D? Oh, okay. Determine the surface charge density, charge per unit area, on the inside surface of the conducting shell. All right. So, let's change this a little bit. Go over here. And let's get rid of some of this extra garbage there and garbage there. And I'm pretty sure I don't need, I probably just redraw this completely. All right. So we now have a conducting shell that is like this. It's not appropriate scale. Will you forgive me for that?
That's fine.
Thank you. So I get, that's 2R, and that's 3R. The inside surface of the conducting shell. If I want that amount of charge, I'm going to choose to evaluate this using a Gaussian surface that is in between the 2 shells. All right? Now, the truth is I want my Gaussian shell to be right up against the edge of the inner shell. But I'm exaggerating my drawing here. But the truth is my Gaussian shell is going to have a radius of 2r. Does everybody understand? But it's right up against the edge. It's right there. So everybody understands, right? Before I go on, I've separated it to show that it's inside the conductor, but it has effectively a radius of 2r. Are we sure? Somebody's going to ask later, and I am going to be mad then. Okay. So, Gauss's law. Q enclosed has to equal 0. We good? That has to be true? So, the charge on the inner surface plus Q has to equal 0. So Q on the inner surface has to equal negative Q. So surface density on the inside wall of the conductor has to be Q inner divided by the surface area. So 2 squared is 4, 4 times 4 is 16 pi r squared. That's got to be the answer. So, am I going to be asked to do number E2? Yeah?
Yes, but also, should we use little q, or is it big Q? Because
It's big Q, because we know the inner charge, because they want the inner the inner surface charge density, right? So this tells me that that extra amount of charge that was added to the conductor must reside on the outside edge, not the inside edge. We're going to see that in a minute. But the amount of charge on the inside edge, in order to balance out the electric field and make the electric field 0, must only be the amount of charge that was attracted there by the positive charge that was located at the center. So it pulled electrons in equal to the amount of charge at the center. That makes sense? That's what's happening here. Okay, so when we do part E, we're going to change the shell now. And I don't know that I can change the shell. I probably could, but I want to move the shell to be on the outside edge. So new shell. And I want it to be just outside. But I want it to have an effective radius of 3r. Everybody okay? We're just on the outside, just touching the outside. So we're not actually out there very much, but we are no longer inside the conductor. That part's important. We're no longer inside the conductor. Is that okay? I don't need to use Gauss's law for this. I'm only going to use one side of it, the Q enclosed side. I'm not looking at the flux at all. The last one I looked at the flux. This one I'm not. The Q enclosed has got to be Q plus Q. I'm not calculating the flux. I don't care about the flux. This is the total amount of charge that has to be on the outer edge. Why? Because I know that's got to be what the electric field is when we're outside. So, what's the surface density? Surface density's got to be Q plus Q divided by 4 pi 3r squared. That has to be true. Why do I think that's true? Well, because it would have just been positive Q on the outside surface. But now it's Q plus Q because all those negatives got sucked to the inside, revealing all these extra positives on the outside. So this total charge on the outside has to include both charges. 3 squared, 9 times 4, so 36. I know you guys don't care about this part, but I know some of the purists out there hate it when I don't finish a problem. So this has to be sigma on the outside edge. Yay? All right, that was fun. That was a lot of fun. I enjoyed that. The charge density has radial symmetry. So each shell would be a slightly different charge density. So if I add up all the shells, that should give me the total amount of charge inside the sphere. So what I'm going to do instead is say that each shell has a volume of 4 pi r squared times dr. Now, you might want to know where this comes from. This might kind of freak you out, but I want you to think about what it means. I'm saying that I get a shell. This is the surface area of the shell. And then I'm multiplying by the thickness of the shell, and that's a volume. Everybody follow along? Let me make sure I got that with everybody. This whole thing is like, imagine if I inflate a beach ball. It would have a surface area of 4 pi r squared. But what's the volume of the plastic that makes up the beach ball? Well, it'd be that surface area times the thickness of the plastic. So dr represents the thickness of the plastic, and 4 pi r squared represents the surface area of the plastic. That okay with everybody? Yes, sir.
No, does this only work because the thickness of the plastic is small enough so that it doesn't make a huge change on the surface area?
That's exactly why it works. Because otherwise I'd have to break this up into little tiny cubes, which would have the same problem. Because the little tiny cubes wouldn't be round, they'd be square. But I'd say the same thing, because they're super tiny and super itty bitty small, it doesn't make a difference that they're not curved. And that's the same thing here. Infinitesimally small, or infinitesimally thin in this case. This represents the volume of one shell. Now, if I want the charge of that shell, I have to multiply by the charge density. Because it's still charge density times volume equals charge. Everybody follow along so far? This has to equal the amount of charge of one shell. Now, there's a lot of shells there. In fact, I have to add up from the very inside to the very outside every single shell. And that will add up all of the charge, Q. We know the total charge is Q. They just want me to have an expression for the total charge in terms of the charge density. So this is what this will produce. Now, this is not a constant. Because if it were a constant, I could just integrate the 4 pi r squared, get 4/3 pi r cubed, and I would get total charge divided by volume. That would be nice. But it's not that. Every single shell is a different charge density. I got to put this bad boy in right here. Or not right there. Right there. Ha-ha. So, and again, for all of you who have had calculus, yeah, this is just mean. It's not terrible. Oh, look at all this. So much work. There. What do you mean, what is that? It's not that hard yet.
That is substituting.
Whoa. Look, I don't care if you had calculus or not. There's not a single person who should not be able to follow these substitutions. I took all of this and put it where rho was because rho is the charge density. That's all I did. So I would expect if I gave this on a test, you should be this far, even if you can't do calculus. What?
But the rho can be, like, if you didn't say that rho was, like, that charge density, it can be considered consistent if it was, like, a different problem?
Yeah, if they told me the charge density was uniform, I wouldn't have done any of this.
Okay. Just making sure, sorry.
Yeah, if the charge density was uniform, that's a different problem. I don't want to spend a lot of time on it, but it would just be the integral of 4 pi r squared dr times rho equals q. Well, 4 pi and rho, if they're constant, come out front, and I get r squared dr equals q. The antiderivative of r squared is 1/3 r cubed. And yes, I expect people to be able to do the polynomial stuff. I add 1 to the exponent, divide by the new exponent, 1/3. I evaluate that from 0 to r, and I still have 4 pi rho. Well, the left side of this is 4/3 pi r cubed times rho, and that equals q. So if I wanted to know what the charge density is, I would just divide by 4/3 pi r cubed. And what do I get? The same thing we've been doing all year. Charge density is total charge divided by total volume. This has to be a result if rho is a constant. The problem is, rho is not a constant. Rho is this effed up thing I got to deal with. Boy, I recorded that. Sorry, internet. I shouldn't say that. I probably should not send this up to the internet.
You already censored yourself.
Yeah, some parents someday.
Did you record last week?
Yeah. Why, did I say anything there I should be ashamed of?
Do you want to know?
Yeah.
We did say the orgy thing.
I'm not ashamed of that.
Oh, well, I feel that's worse than the whole effed up thing for the internet. I mean, anyways, not really.
It's just protons and neutrons, dude. Don't read too much into it. Oh, I forgot. High schoolers. Everything is read too much into. If there's... Oh, you said that word. Oh, no.
No, I don't care. I just
Oh,
thought
okay.
if you thought effed up, that anyway.
This, and this, all constants, right? They're all the same. They don't change. So 4 pi rho naught can all be brought outside the integral. Distribute this, and I will get inside the parentheses r squared minus r cubed over r dr. Any questions about that? Okay. Still from 0 to r. Okay, now we get all the way to here. Here's where you folks who are just learning calculus, this is where I can let you off you can just take the off ramp. You should get to this point and then be going, okay, now I don't know what the hell I'm supposed to do. But that's really, really a bit of a coward's way out because this is a polynomial. And my expectation is that we can work the polynomials out. They're not fancy. Antiderivative, term by term. R is important, right? This tells me R is important. So I'm going term by term.
Thank you.
You're welcome. I'll go to the first term, which is r squared. I will add 1 to the exponent, r cubed. I will divide by the new exponent, 3. That's first term. Put a negative sign in there, go to the next term. The next term is r cubed over r. So this r is just a constant. Put it out front. Take my r cubed, add 1 to it, r to the 4th. Divide by the new exponent, 4. That's the last term. That's it. This is the antiderivative, evaluated 0 to r. Don't forget my 4 pi rho naught. Okay, the heavy lifting. Now you must come back on to the highway so we can finish. We just put in r and 0. Now I'm looking ahead. I see putting in 0 is just going to zero out the whole thing. So not worrying about 0, I'm just going to put the R in for both of these values. And that should be my answer here. So 4 pi rho naught times R cubed over 3 minus, oh, it looks like R cubed over 4. We all seeing that okay? So keep going. This all equals Q. 1/3 minus 1/4 is 1/12. Pretty sure. Last time I checked. So this should be 4 pi rho naught R third over 12 equals Q. And can you all follow this? Cancel 4 with 12 and put a 3 here. Still okay with all of you? My recollection is I'm supposed to be solving for rho naught. So although I have this, what I really want to do is now get rho naught by itself. So I will have to multiply everything across. So it looks to me like I'm going to have 3q divided by pi r cubed equals rho naught. Sure hope that's the answer.
It is. That was the goal.
They gave us the answer. We knew what we were shooting for. I just don't remember if it was there or not. But looks good to me. It has to be a charge density. So I can check to see if it kind of works out. And I have coulombs over meters cubed because pi doesn't have any units. So that makes a lot of sense to me. What's funny is there's a 3 in there. Do you see it? Let me show you something else that maybe you don't see. Erase the 3 for just a minute. It would be the same equivalency if I put 1/3 pi r cubed here. You know why I'm doing this, right? If it was a solid charge density, it would have been q over 4/3 pi r cubed. But because the charge density tapers, we get a value that's slightly different there. But the geometry still kind of works out to be very similar. Interesting? Maybe. I think so. All right, good. That was fun. I enjoyed that. I always love a good, solid calculus question. And this one was kind of interesting. It's not what you learn in calculus, but I like this anyways. You learn how to do the one step in calculus. They're all on, doing this one thing. Let me get there. Right there, this one jump from here to here, That's what calculus it spends all of its time on. But the thing is, that's not why calculus was, put together. It was this stuff here. That's the hard stuff. Packaging it, getting it to this point, figuring out how you're going to add it all up. That's the hard stuff. Like I said to you, all calculus does is give you a set of skills for making this one step from here to here. But getting to this, that's work. That's imagination. That's interesting. I like that stuff a lot better. The rest of it, you can just put into calculator. It'll spit out the stupid answer. But I don't know. Anything else on the homework you would like me to discuss? I am happy to do so. Let me say the problem again so everybody gets it. It says a 10 nanocoulomb charge. So here's our cube, is centered inside a cube of, 20 by 20 by 20? Or 2 by 2 by 2. So there's a cube here. And that charge is centered inside the cube, 2 by 2 by 2. And we'd like to know how much flux passes through one surface. Well, would you agree that the entire flux is going to be Q over epsilon naught? Would you also agree that since we're at the center of the cube, every surface will have the same amount of flux? Because it's symmetrical? How many sides are there to the cube? It's going to divide the flux by 6. That's how much flux must pass through one side of the cube. So that's what I would do. And yeah, this definitely is the kind of multiple choice question I would expect. They had one like this, but they put the charge at a corner. And they said that the center of the cube passed through the center of the charge. So 1/8 of the charge was inside the cube. That was a question a couple years ago. It was an FRQ though. I'm not giving that to you tomorrow, but it's one of those wrinkles, you know.